So today last class we wrapped up with the SN2 reaction, and today we're moving on to the SN1 reaction. So again, we just covered this. So the SciComm assignment, sorry Nulia, yes, the SciComm assignment is due on Blackboard by the 26th, but there is no penalty if you submit it before the exam. So there's no late penalty. Yeah, anytime before December 12th without any penalty. Thank you, Jaffer. But it is due on the 26th because it's an evaluation. Evaluations must be due before the 26th. And I think you should be able to upload multiple files. It can be basically anything to do with organic chemistry. It's very, very loosely done. I'm seeing all sorts of different things coming in on this. I've seen some poems about bonding. I've seen some infographics. There's videos about specific chemical things. There's videos about specific chemicals. There are people producing short stories. There are people producing dances. There are people producing musical pieces. I've seen somebody basically thinks the infographic isn't enough space for them to do what they want to do, so they're producing pamphlets. People creating card games. So it's very, very, very broad. It needs to be in chemistry and organic chemistry. It can't be about biology. Now, it can be about biology applied to organic chemistry, but it does need to be at the molecular level, and it needs to talk about some form of mechanism. And a lot of biology does do that, and you can sort of focus in on something in specific you're interested in biology that's at the organic chemistry level. That's fine, but it does need to be on the organic chemistry level. So Andrew said, what reaction takes you from an ester to an aldehyde? You can do that using a reagent called Dibol, which we haven't covered in this class. So another way you can do that is you can reduce the ester all the way down to the alcohol using lithium aluminum hydride that we did cover. And then you take the ester back up to the alcohol back up to the aldehyde using PCC or PDC. Yes, the mark will still be inputted. The final grades might take a little bit of time to come through. It depends how much grading and how all that works out, how long that takes to do. But hopefully, we'll have those before Christmas. The final grades need to be submitted by January 6th or something. But hopefully, we'll get them in before that. Please don't submit 2 assignments. Just do one. If you have 2 really creative ideas, give one of those ideas to your friends. Unless if you're thinking about putting in effort for 2 assignments and the amount of effort, and you have 2 good ideas and you're really excited about and you want to do something, you're going to get full marks on one of them. You will not get full marks if it's a weak like if it's sort of a weak slapdash assignment that you threw together at the last minute. But it would be very Sarah, yes, you certainly. So Sarah asked, "Can I make a small compilation of videos since I can't decide which one of them to do?" Yeah, you absolutely can. And what you might want to do is upload a file with like links to the YouTubes for those. You can or upload the file to the links to the TikToks if you prefer doing that. That can work really, really well. If you want to do multiple ones, absolutely. I'm never going to say do less. I am going to say don't knock yourself out on this one. I'd really prefer you guys spend a few more hours looking at mechanisms than an extra hour doing extra stuff on this that's beyond the scope of what you need to do. Like if you're having fun doing it, by all means, please do it. Have as much fun as you want, and I really want to encourage that and support that. But and that does put you into a better running for that extra 5 bonus percent if you're going above and beyond. But you don't need to go above and beyond to secure the 5%. Yeah, probably uploading a file with a YouTube link is probably the better way to submit a video rather than sort of uploading a video. I don't think Blackboard has a maximum, but if 340 of you all try to upload a 1 GB video, we might really test that theory. Yeah. Okay. SN2s. So we talked about this last class. This was the direct displacement. So again, remember, in the SN2 reaction, the nucleophile is coming in. Yeah, of course it is. Bhavin just said the maximum is 100 megabytes. So obviously you might have tested this already. So links to YouTube videos is a good way to go in the file, and then you can also in that file you can also include any kind of comments you want to make and anything if you think it's unclear and you want to kind of provide a little bit of added context because it's really abstract. Yes, and you can make compressed zip folders, though there is a limit to how much some things get compressed depending on the file type. So, as we're not going to talk about nucleophilic, we're going to talk about file types, right? The other thing is I am a PC user, so it'll be really good if you do submit something from a Mac, please don't use Pages. I'll come after you. Just submit it as a PDF or a docx or a doc. Because I have nothing that can read Pages. So substitution occurs, everything else is different for the SN1. There. Need to get past slide number 2. So in the SN1, what we have instead of having both molecules coming together in a transition state and in that rate determining step, and we covered this when we did the intro to substitutions, all we have in a rate determining step is the leaving group wanders off and you make a carbocation. So this is an intermediate and it is formed. And then your nucleophile can approach from either side. So in the SN2, the nucleophile came in opposite the leaving group. In the SN1, that's not the case because you go through this flat intermediate. And at this point, the nucleophile can choose to come in from either the top or the bottom side of the molecule. So what ends up happening is in the reaction coordinate, what happens in the reaction is the slowest step is generating this pair, this ion pair, because you're breaking a carbon something bond. You're going to form a carbocation. That is going to be slow because carbocations are not stable. So this bond gets longer. Using my mouse, but my mouse isn't connected. This bond here gets longer and longer and longer until it breaks completely. Then in the second mechanistic step, nucleophile comes in and attacks the carbocation, giving us the two products. And this is reflected in the energy diagram. So we have a starting material. We have this intermediate that is the carbocation. It's much higher in energy. Then we have the product. And we drew this and we went over this when we started introducing substitution reactions a while back. So the SN2 reaction relied on the concentration of both nucleophile and electrophile because the rate determining step had both the nucleophile and electrophile in it. The SN1 reaction, it doesn't matter how much nucleophile is present because the only thing that matters is how fast that leaving group leaves. So this is actually a question that went around, that we discussed in a graduate class I took on physical organic chemistry. And the professor for the course went around to all of his colleagues in the department, all the other chemistry professors. And he asked them this question, basically, which is, okay, so why does a first order reaction depend, why does the rate of a first order reaction depend on concentration? So when you think about this, if you've got one molecule in a container, a huge container, and all that matters is how fast that molecule falls apart, it's not going to fall apart much faster if you put it into a smaller container or make the container bigger. So why does the rate of the reaction depend upon concentration? Does anyone have an idea on that? Because the concentration is in the rate law. But there's no more particle collisions because there's only one molecule that's falling apart. So there's no need for, exactly, higher concentration is more important for bimolecular reactions. So, but it doesn't need to bump into anything. All that's happening is this molecule is breaking apart on its own. Noah's closer on his discussion, saying that there will be more molecules, so a better probability of it happening. But let's remember what rate is measuring. The rate of an individual molecule breaking down is the same regardless of its concentration. But rate, when we're talking about chemistry, we're not measuring individual molecules. We're measuring moles per liter per second. And so the trick question component of this is that the reason the rate goes faster when you increase the concentration is because the molecules break down faster. It's because there are more of them. So going with Noah's discussion here, if you've got 5 molecules in 1 liter or 1 molecule in 1 liter, if the rate is 1 molecule per second, 1 molecule per liter per second, the rate's the same for both of those, but with more molecules present in there, you're going to have more of the molecules turning over. You're going to be making product faster because there's more of them present to do that turnover. Because in 1 second, you'll have, one of those 5 turning over and the other one, or 5 of them, and the other one only 1. So rate measurement is concentration per second. It's not molecules per second, it's concentration per second. And so that's why concentration matters for this. But concentration doesn't affect the rate at which an individual molecule falls apart. The molecule falls apart at the same rate. One molecule falls apart at the same rate regardless of what the concentration is. And if you're able to follow that, and I think Noah's discussion is comment in the chat is very, very correct. You're doing better than 50% of the faculty at the University of Ottawa did on this question 10 years ago. So good for you. Because it does come down to thinking about what are you measuring? What are the units of these kinds of things and why the units matter? So if we're talking about the stereochemistry, a clue for the SN1 reaction is that you get racemic mixtures. And I'm going to refine this a little bit. You get they're kind of 50-50, not 5-50. I'm going to say 1-to-1. I want to say epitopic at the reaction center. The reason I want to be a little careful about the word racemic here, I'm using a different word, which we haven't seen so far, is because it's only racemic if there's no other chiral center in the molecule. If there's another chiral center in the molecule, then it's not racemic because there's another chiral center in the molecule that hasn't been affected. So what we're doing here is you're going to make a 50-50 mixture of the possibilities that at that stereocenter where the reaction is occurring. And that's an epitop. A molecule is epitopic at a center if it's kind of got both diastereomers or both versions of that stereochemistry at that site. You don't need to remember that word. You could say it's racemic at that center, and I'll know what you mean. But racemic is a property of a molecule as a whole and not of a carbon in specific. So if there was another, for example, if there was another up group here, this would be up either way. And then it's a mixture of R and S at this center, but it's not a mixture of enantiomers because and these aren't racemates because one of the chiral centers isn't flipped. So you just be a little careful with that. So racemic mixtures are formed, but just be careful that that's only true when there's no other stereocenters present. But it still means that your chiral center, that particular center, is a 50-50 mixture. Yes, you can actually have, Emmanuel just asked, will one probably be favored if there's one group blocking one face? Absolutely. If you're blocking close to that site, you are going to have a stereoselective reaction. You're going to differ from that 50-50 because now they're not equal. So in actual experiment, if you want to figure out the reactions SN1 or SN2, do you just look for enantiomers in the final product? that actually can be really useful. That can give you a lot of information on that. And we're going to come back to that idea, Mohammed, in 3 lectures when we start comparing everything together and really trying to dig into the fine-grained detail here. Because what we're seeing is these arrows are simple. Compared to what we've been drawing for weeks, and keep practicing that stuff, these arrows are really, really simple. And I will be posting a video on the mechanism of ozonolysis that we did during office hours. I'm just going to put that up there. It should be up there soon. But it's the details of which one of these you do that's really tricky with these things. And that's why I've kind of left them for last, because we're kind of tying everything in a course kind of gets tied together when we're analyzing these things. So in the SN1, because the intermediate is planar at sp2, and it's got the giant p empty p orbital, you can attack either lobe of the p orbital and get your product. So either you can attack from the bottom or from the top. So even if you start with the chiral center here, that stereochemical information is lost because there's a planar intermediate. It's sad to lose information. So an optically active reagent will always give optically inactive products in an SN1 reaction, assuming the reaction occurs at the only stereocenter in the molecule. So the effect of substrate on SN1. So if we remember how this worked for the SN2, what we wanted to do was make the leaving group accessible. In the SN1, what we want to do is we want to stabilize the carbocation. And that comes down to the mechanism, right? In the SN2, the nucleophile needed to approach the electrophile from the back end from where the leaving group was. So how easy it could approach, how blocked up that site was, fat cat, skinny door thing, really determined how that worked. Whereas in the SN1, all that matters is how stable is that carbocation. Because all we're trying to do is lower the energy of that intermediate to make it more accessible. And so the more stable the carbocation, the better. So what we need to be very careful about here, what I'm going to do is I'm going to highlight this, I'm going to put a little asterisk next to this, is in general, tertiary is more stable than secondary, is more stable than primary, is more stable than methyl. And tertiary is much more stable than secondary, and secondary is much more stable than primary. Okay. Now, what we have here, and why I want to be really careful with these comments, is this resonance here. So what we have is we have resonance, and I'm saying resonance is less stable than tertiary. And what you have to do is be very careful with that statement. So in this case, these were both very carefully selected. This is, and it's very, I really hate this example because these are actually the only two where this is the case. Any other resonance is going to be more stable than tertiary. And what I mean by that is, let's consider this molecule, which looks really close to this guy. But because this is a secondary carbon, this now becomes more, this is more stable because of that secondary carbon. And secondary versus tertiary is different from primary versus tertiary. And we have all the resonance of that benzene ring. And the same thing with the allyl group, this thing on the bottom there. If I turn it into that, now all of a sudden this is more stable. Now another example I want to show with this too, I'm going to put it up in this top right corner, is let's say we had something that was, like this. And you're going, okay, well, it's resonance, but it's primary. So it falls into this box here. But I'm lying to you because it's not primary. because this is in resonance with the tertiary carbocation that has resonance. And this is really very good. This is ridiculously stable. So I am going to put in all other resonance is better. It's almost like we picked the only two examples where it's worse than a tertiary to put in that box. We still see this in some textbooks. So I really want to highlight that this is just a key. These are like a key exception. Resonance generally gives you better than tertiary because in many cases you have tertiary plus resonance, which is really awesome for stabilizing a carbocation. And I know we've talked endlessly about resonance and stabilizing things, so this should be like second nature to you now. If it's not, go back and please look at the resonance stuff because it matters. So SN1 reactions and a rate of SN1 reactions is determined by how stable the carbocation is. So I don't know if there's any other way to write this. Primary carbocations are so unstable that if you don't have resonance, you don't have a chance in hell of getting an SN1 reaction. A methyl carbocation is even less stable than a primary carbocation because it has much worse hyperconjugation. And so there is no chance in the length of the universe to generate CH3 plus from just a leaving group leaving from an SN1 reaction. There are ways to do it, but not this way. And a primary is very unlikely to happen. And that's good because primary and methyl leaving groups are the best for SN2. And so now the SN2 can happen there. And we're going to come back to this because it's not a paradox and it's not convenient. It comes down to some basic facts. But we're going to reanalyze this in a bit. Yes. So Emmanuel asked a really good question, which is on this slide at the top, even if the leaving group was on a primary carbon, would be added to the tertiary one? Yes. So we're going to do that example. But let's say you had a bromine on this carbon. The nucleophile would add to the tertiary center because you make that intermediate. The bromine leaves to infinity. You make the carbocation, and the carbocation sits at the tertiary spot. If it's so unstable, why doesn't the leaving group want to leave? Do you mean there's a lot of double negatives in there? Do you mean if it's so unstable, why does the leaving group want to leave? Oh, it's very stable when it's attached. It's once it leaves, it makes a carbocation. That's what makes it unstable. So a leaving group on a primary, like a bromine, like this is perfectly stable. Nothing wrong with that. This doesn't go to that. That's really unstable, so you're not going to have it leave, so it won't do an SN1. And I know Nicole got that before I drew that in, but for anyone else who was confused, this would be good. So last class, we were talking about how we wanted aprotic solvents for the SN2 because what we wanted to do was not stabilize the charge of the nucleophile. We wanted a naked nucleophile that was negative and unhappy about being negative, and it would react. So to do an SN1, we want a protic solvent. Why do we want that? Because generally, we're going to have weak nucleophiles to do SN1s. We're going to talk a little bit about why. But that normally means they're neutral. So what we want to do is we want to stabilize that high energy intermediate, and that's a carbocation. And how can we stabilize a carbocation? We can stabilize it through hydrogen bonding. Or rather, we can stabilize it because the heteroatom attached to the hydrogen can stabilize a carbocation. Well, that's what we see here. So for an alcohol, you're not hydrogen bonding per se, the hydrogen's out here. But because this can hydrogen bond, this is a very, very polarized bond. And so this oxygen here can stabilize the R group, and this one can, and this one can. So you have stabilization occurring because your solvent is so polarized that it can stabilize the carbocation as it's being formed. So whereas the SN2 liked polar aprotic solvents, the SN1 likes polar protic solvents. They both like polar solvents. Just the SN1 wants them more polar, and you get them more polar by having them protic. And that's because we want to stabilize charges. Whereas in the SN2, we want to destabilize charges to make them go better. So what we were just saying is the rate determining step is decided by the electrophile, the nature of the electrophile, how fast the leaving group leaves. So it doesn't matter what the nucleophile is. If the rate determining step of a reaction depends on the electrophile, it doesn't matter if the nucleophile is iodine, water, ammonia, my dog, if my dog was a molecule, all those would react at the same rate because the nature of the nucleophile does not affect the rate of the reaction. The only thing that matters is the nature of the electrophile and how fast that leaving group leaves. So you can have really, really weak electrophiles do SN1s. I'm going to tease this idea down here that a good nucleophile will tend to make the mechanism go more SN2-like, because a good nucleophile is not going to wait around for the leaving group to leave on its own. It's going to push it out. Unsurprisingly, the better the leaving group, the faster the reaction, because so far with the intermediate, remember, starting material, intermediate, product, and we've been sort of thinking, okay, let's say starting material is this, the product is, I don't know, let's put an ammonia on there. Your intermediate is going to be the carbocation, which I should draw as, planar. So far, we've been focusing on the carbocation. That's what we should be focusing on. Absolutely, it's the most important part. But there is another component here, and that's the Br minus. And so the more stable that anion is, the lower energy that intermediate is going to be, because that intermediate includes the energy of both the carbocation and the anion. So the better the leaving group, the more stable the leaving group, the happier it is with the negative charge, the lower energy that intermediate is, and the faster the reaction, because the lower this activation energy, this value here is. What stabilizes? So Janek asked, what stabilizes leaving group more? Does electronegativity, resonance, or size matter more? All the same things that make for a weak base. So when we were talking about the acid base and what stabilizes the negative charge, all the same things. Leaving groups are it's all the same analysis. And I don't mean it's analogous to the same analysis. It is the same exact analysis. It's all exactly the same things. So what matters most generally is which atom has the charge, and what matters more there, size or electronegativity? And the answer is both. It really depends where on the periodic table you're comparing it to something. Then does it have resonance? Then and those kind of things can play in. And then is there inductive effects? And so all those same things matter. There's nothing new to your analysis here. So if we compare, just in a quick little table, what's the most common weak nucleophile for SN1? Water, probably. When an SN1 happens, there's always some water around because you weren't dry with your conditions, and so water comes in as a nucleophile. So if we're comparing SN1 and SN2, the SN2 is favored by a good leaving group, so is the SN1, because the nature of the leaving group matters for both. Accessibility was really, really important for the SN2. We did not want a tertiary carbocation or tertiary carbon with a leaving group on it because the nucleophile couldn't get at the tertiary. The SN1 wants the opposite. It wants a stable carbocation, so tertiary is great. You want a good nucleophile for SN2, you don't care what your nucleophile is for SN1. You want aprotic solvents for SN2. You want polar protic. I don't know why I didn't write protic. Solvents for SN1. The product proceeds by inversion for the SN2, and you have a racemate for the SN1. Just gonna mute somebody. There we go. Unless that was a cry for help. Like it was something other than organic chemistry. Because if it was a cry for help for organic chemistry, I guess you're in the right place, sort of, but not really. Let's look at a few of these examples. So if we have, so there's a pair here, N-propylbromide or allylbromide. Which one will react faster by an SN1 mechanism? So to answer that question, the first thing you need to know is what are these and draw them out. So I'll give you a second to draw those out and give out your guess. I mean guess, not guessed. Okay. N-propyl, the N, if you don't remember, just means normal. So linear. So it's not like isopropyl. There's no sec-propyl, but could have been like, where's the bromine? The N-propyl. I would never write it this way. I'd always write 1-bromopropane. This is a really stupid way to write 1-bromopropane. I wrote these things up for chemical engineers, and they write things like this. Allylbromide, if you don't know what that is, and again, I would not write allyl because we haven't discussed that a lot. This is the allyl group, but this would be, 3-bromopropene. Not a bad idea to know what those are. I'm going to generally give you structures, though, because I don't care very much about naming. RNS is important, but all these details like this is pretty much a waste of your time. So what's not a waste of your time is figuring out which one of these is going to react faster by the SN1. So if we think about what's happening in the SN1, leaving group leaves to infinity in the first step. And what determines the rate of the reaction is how fast does that leaving group leave. So if the leaving group leaves, what I'm going to have here, carbocation. What I'm going to have here, carbocation. They both have bromides. They haven't told me anything about the solvent or anything else, so I assume it's all going to be the same. If both bromides, the bromides cancel each other out, so I don't need to consider those because those are the same. So I'm left with considering the structure of the electrophiles. And they're both primary electrophiles, primary carbocations, except this one's not really a primary carbocation because it has a really good resonance structure. Well, it's got a resonance structure. Really good, I think, is pushing it a little bit. Primary in resonance with the primary. Now, this was the one where I said, hey, this is not as good as a tertiary. This is the only exception to that rule. Whereas this is just a primary carbocation. So this one is better. That's more stable, which means it's faster to form. Because that carbocation is more stable, because that intermediate is lower in energy. I have overwritten this. That is that. Okay, so this is a slightly different question. So predict the compound in each pair that will undergo Solvolysis in aqueous ethanol more rapidly. So what you need to know is what Solvolysis means. And you need to pull that word apart, and it means solvolysis. Lysis means breaking. breaking with solvent. So which one of these is going to react faster with ethanol? And since this is a lecture on the SN1, we're going to talk about why you can tell this is SN1 later. But all you've got is basically what this tells you is that the reaction is, for example, in ethanol goes that's what that effectively means. We're cleaving this in ethanol, solvolizing, not solubilizing, solvolizing. So it's chemistry rather than just changes of dissolution properties. And so your solvent's the same. That means your nucleophile is the same. You assume the same temperature. You assume everything else is the same. It's the same leaving group. So again, the only difference is basically asking us, is there a difference in the stability of the resulting carbocation that you get when a leaving group leaves? And so you draw what you get when a leaving group leaves in both cases. And hopefully you take a quick look there. You go, okay, got nothing, no induction, charges on carbon on both of them. There's no resonance. So there's nothing I need to consider stabilizing these charges out of the normal. It's primary versus secondary. Faster. Now, this one's asking which one's going to break faster. I'm not even giving us a nucleophile here. They're just like we're basically saying which of these is faster under the SN1. That's just what Solvolysis is. That's what's happening. It doesn't. You actually don't need to know that's what's happening to answer the question, but yes, yeah. So this one, which one will undergo Solvolysis more rapidly? Again, we're indicating SN1. We're going to come back to why that's normally SN1 through Solvolysis. Now, you're going to make the same carbocation in both cases. So what this question is essentially asking is, if the carbocation is the same, which one is the better leaving group? Because the better leaving group is going to leave faster. So the question comes down to, is Br minus more stable than Cl minus or vice versa? Thanks, Mohammed. Mohammed's off the bat really fast, and Victoria piles in for the victory lap. And yeah, it is bromine. Br minus is more, as you go down a column, you stabilize negative charges better. And so bromine, although less electronegative than chlorine, stabilizes the negative charge better than chlorine because it's bigger. So for each of the following reactions, give the expected substitution product and predict whether the mechanism will be predominantly first order or second order. So let's pull apart what this question's actually asking. It says, give me the product of the reaction. Cool. And when they say predominantly first order or second order, what they mean, is it SN1 or is it SN2? So this one they ask 1 iota, 1 methyl cyclohexane plus ethanol. So first thing we should do is draw out 1 iota, 1 methyl, 1 cyclohexane plus ethanol. Okay, so now if we're thinking, and they're saying substitution. So I'm looking around to do a substitution, and the only thing I've got that can do any kind of substitution is the oxygen. There's the only thing with lone pairs. So I expect that the reaction is going to give me that. Plus formally HI, although probably H plus I minus. So the question is, does that go by first SN1 or SN2? And there's a lot of things you can ask yourself here. You have to look at all these different things and figure out what's more likely. And you're playing a game of probabilities here. So remember what you need for these two. For the SN2, what you want is you want a strong nucleophile. You want an accessible carbon with the leaving group on it. You want a polar aprotic solvent. Those are the big three. And you want a good leaving group, but you want a good leaving group for both of them. So that really doesn't help you. So if we're looking at this, and I'm looking at it, I'm going, well, okay, that's a tertiary center with a leaving group. This is a weak nucleophile. And why is it weak? Because it's not charged. Neutral things normally kind of suck as nucleophiles, unless you're phosphorus or sulfur. But oxygen sucks as a nucleophile if it's neutral. So the tertiary indicates SN2 is not possible on a tertiary. And a weak nucleophile is very unlikely to do an SN2 because it's weak. So this is all looking SN1E. Everything is pointing us towards the SN1 here. What about this one? So again, do the same kind of analysis. Look at your electrophile, look at your nucleophile, and think about what you want in terms of mechanism. Okay, any guesses? Yeah, it's a negative S. It's S minus sodium plus. So the cool kids are answering in the chat. It doesn't indicate what the solvent is. Emmanuel is stuttering his answer a little bit. SN2. It is an SN2. We have a strong nucleophile. It's negatively charged. It's reactive. It's not going to wait around politely for the leaving group to leave. It's going to barge in and knock that leaving group out. We have a primary leaving group. It is on a primary carbon, right? If this leaves, you will get a primary carbocation, and that sucks. Primary C plus sucks. So it's not likely to leave on its own. It needs to be pushed. And if it needs to be pushed, and we have a good pusher because we have a strong nucleophile, we're doing SN2. And we can draw the mechanism. Whee! We get our product. There are tons and tons of practice problems in the text. I also gave you a ton of practice problems, I think, in assignment 3 or 4. Yeah, it does form any. You know what? I'm ignoring sodium. It's spectating. and I'm not paying much attention to it. You can write NABR if you like. That's completely correct. Yeah, so Mohammed, you're asking the tough questions there. So leaving groups are things that are stable when they're negatively charged. Nucleophiles are things that want to react with the nucleus, so normally it's an unstable negative charge. So neutral molecules tend to be the electrophiles. Bonds to halogens, chlorine, iodine, bromine are the good leaving groups. Because that's a phenyl ring. I could have drawn it like that. The next slide or the slide before? We can't, mostly halogens, I'm gonna show you an example of another one in the previous slide before we wrap up for the day though. Okay. That one? Are you good or do you have a specific question for this? Cool. Okay. So what I want to talk about is so far we've seen phenol, so this is phenyl. Like, let's just be clear. It's called a phenyl group. And that's like an aromatic, it's like a benzene ring that's attached to something as a phenyl group. Phenol is that. Phenol is not a thing. So let's say we had we wanted to do this. Well, if I push the arrows going the other way, that's easy. OH minus. Theoretically, it's easy. Practically, it's actually harder than that. But theoretically, it's easy. That makes sense. OH minus comes in, displaces I minus as a leaving group. Everybody's happy. But I minus coming in and displacing OH minus does not make a lot of sense. So what we need to do is we need to find a way to make the OH into a good leaving group. And what we're going to do is we're going to cheat. I'll stick with this one. This is called, it's got a longer name, but I'm not going to use it. Trifluoromethane sulfonate chloride, sulfonyl chloride, but I'm just going to call it triflic chloride. And if you look it up online, you'll see that. And normally there'll be a really weak base present. My favorite weak base is imidazole. I'm going to leave the mechanism of how we go to the intermediate to you. It's not tricky. I'm leaving it because we're basically out of time. But now let's think about what's happening here. So OH is a bad leaving group. It's reactive. But I like the look of that leaving group. So this should seem somewhat familiar. It should look a bit like sulfuric acid. And we know sulfuric acid is a really strong acid, and that means that the conjugate base is a really stable molecule, except this is far more stable than sulfuric acid. This is probably the best leaving group. I'm going to say best normal leaving group. There are better ones, but they're really weird and they are hard to make. And it's because this negative charge is shared amongst all three oxygens, and you have a huge inductive effect from the CF3. Over here, plus HCl. So it's going to combine with that chlorine. And that's actually going to exist instead as the imidazolium. So the imidazole is going to react with that. So what you're actually going to have is that. But that's okay. Yeah. Mesolates and mesolates and tosolates are the same thing as triflates. This is called a triflate. I'm going to mention mesolates and tosolates later, because we're going to come back to this idea again. But I just want to put this bug in your ear that we can take an alcohol and we can turn alcohol into a really good leaving group. So Janik, you're way ahead of the rest of the class, so I'll talk about mesolates and tosolates. Yeah, all these are SN2s. And what gives us a clue that these are all SN2s is this is all happening in a primary carbon, so it's very unlikely that there's any SN1 chemistry going on here at this primary carbon, because you're not going to make any carbocations. So we need to find a way, if we can't displace something with something, can we turn something into a better leaving group? And yeah, we can turn alcohols into better leaving groups. We can actually do something really similar with nitrogens as well. So that's time. We're at 2:22. I will stop recording and let everyone get on with the rest of their Wednesday. Have a really good Wednesday.